So let me open sketchbook. All right, so Fourier's law. What does Fourier's law tell me? What is the fundamental message of Fourier's law? Anybody? Temperature gradient does what? So if I have a temperature gradient, I'm going to have heat flux or flow. Basically, we measure it typically per area, so we refer to it as flux. And that flux will go from area of higher temperature to area of lower temperature. So essentially against the gradient, because all of the coordinate systems that we know, they point from low to high, and I'm always flowing from high to low. So basically, I know that Q, okay, which is my flux, will be related to the gradient. It's going to be in a direction opposite of the gradient, okay? And the simplest ever relationships that I could ever have is the linear one. So I have a coefficient that we refer to K, and that is our thermal conductivity. So it is, in essence, a very simple observation. I have differences in temperature, they're going to try to equilibrate, and the simplest possible way I could model it is that they're going to equilibrate proportionally to the actual gradient of that temperature. Okay, so basically this is my Fourier's law. So now I have a fluid, and there is a difference in temperature within my fluid. Is Fourier's law enough to describe what will happen as a result of that temperature gradient? So what else do I need? So Fourier's law is essentially, it's enough for a solid, right? Okay? I have solid, I basically know pretty much everything that is going on based on this flux. But now I have to add the fact that in a fluid, I also possibly have a moving fluid. Okay? So if there's no velocity grade, then again, Fourier's law is enough. But if I don't actually have a static fluid, I have the one that moves. Then if I'm standing in this position and watching a river flow by, at every moment I will see a different fluid packet, shall I call it, okay? I will constantly be sampling different fluid at the same location, so I actually have to account, in addition to heat that is there simply because of heat flux that is there because of the differences in temperature, I have to account for stuff that simply flows in by convection. Okay? So there's certain energy that will flow in and that I have to account for. So basically, first part that we actually account for is simply this convective energy that might actually flow in. So I'm going to call this convective energy flux vector. And that stuff that flows in basically has a direction of velocity, and that's also the rate at which it flows in. But what flows in? Energy. How do we quantify energy? One part is the kinetic energy, right? And the other part we refer to as simply internal energy. So basically every fluid packet that shows up will have 1/2 rho v squared, which is basically kinetic energy density. and rho times u, which is my internal energy, and the little hat above this u refers to per volume. Okay, so I'm normalizing things per volume. All right, so basically this is the convective flux energy vector. And now if I was actually interested in watching my control volume, whatever that control volume might be, how do I quantify, if this is my energy flux vector, what flows in through the surface of that volume? How do we do that in general? Divergence will have something to do with it, but I have to have a dot product with normal. So basically I'm going to collect only what comes in normal through the surface. Okay? So the moment I have some flux vector that describes flux or anything, it could be energy, it could be simply velocity and the momentum that we had before. Okay? I'm going to do a dot product with the normal to see the projection that is normal to the surface that I'm coming through to actually quantify. So just as a reminder, basically amount of energy that will flow in. So I take this V and I do dot normal and times the area of whatever little surface that I'm looking at. So this is going to be amount of energy that flows in through the surface of area ds and whose normal is n. And then where the divergence comes in through, that's a good instinct, is if I was actually collecting over the entire surface, I would integrate this. So I would have a surface integral, okay, of this. And when you do that, that basically then the divergence theorem allows you to relate that per, so if I was looking around a little ball around a point, and I integrated around that ball with that surface, and then if I was attempting to shrink that to a point, I would get a divergence out of it, okay? So that's where divergence and how divergence is related to integrals over the surface. All right, and is this all? What else might happen? Work of basically, there's friction working on within my volume. Even if I just flow in, there's still some layers that are moving at different velocity, okay? And that is doing work on my fluid element and might heat it up, okay? We kind of have already the notion like that viscous friction could literally heat up my element, and we will quantify that as the work of the molecular forces. And if we remember, the way you get work is you have a force vector and you dot it with the trajectory, okay, along which you're going to do that. So basically, in general, your work would be, work in general is F dot trajectory vector R, okay, and the rate of work is basically F dot dr dt, so that is F dot v. So basically, if I'm looking at the molecular forces, then I'm going to be looking at the tensor P dot V. And result of this is a vector, we have to remind ourselves, and that's going to be the last piece of my energy flux vector. So when I put it all together, 1/2 rho v squared plus rho u V. So this is my convective energy flux, plus the molecular work, and I'm writing it with square brackets just like in the textbook to indicate that it's a vector because P is a tensor. I could also then do this, okay? And plus Q. And what is P again? Do we remember? Plus viscous tau. So sometimes, okay, this is actually added to this part. I can or don't have to write delta here because delta V is going to be V. Plus tau dot V plus Q. And then this portion here can be written as rho U plus, I'm going to write rho times specific volume, which is basically rho times specific volume is 1, times PV. So that is equal rho plus U plus PV V. And this term is basically referring to the entire heat content of my system and is called enthalpy H. So this is enthalpy again with the little hat, so that means per unit volume. So this is just rewriting. And that will actually, there are expressions or thermodynamic expressions that will help us calculate this when we need this. So we are actually going to more use this part or this version of the formula than the previous one, though they are equivalent. So this is 1. This is the original. So this is energy flux vector. So again, nothing has really changed. Just like in momentum transfer, we had to account for stuff that is simply coming in, and for any friction within my volume that might transfer to heat. Okay, so this is simply conversion of energy. So this energy flux vector basically quantify any kind of heat or energy related changes that I might have within my volume, especially if I'm standing still and I'm not actually moving with the coordinate system. Yes?
I don't understand why do you multiply that with the velocity vector, the first part, like rho v squared plus rho u? Why is that multiplied?
It's always like, just like momentum. We had multiplied it with momentum as well, just simply because V is, yes, rho V. So V is simply the rate that stuff is coming in. Okay? So velocity simply quantifies the rate of the stuff moving into my volume.
So that's
and then the rest is what is actually moving into my volume. So now I'm actually not looking at rho V, but I'm looking at the energy. Okay? So this is literally what is flown into the volume. So whatever it is that you might model, this would be the same, essentially, because velocity quantifies the rate of stuff moving at each point. All right, so this is a quick review of the main formula, and this is sort of this energy flux is the main formula we will need. So let's actually now do some shell balances and solve a problem. So this is steady state shell balances for heat transport so in BSL, please refer to chapter 10. This is the chapter equivalent of chapter 2 for momentum. So now we're actually going to get practical. So if I actually look at a small system or the geometry where I'm monitoring my heat transport, I'm going to do the net balance of energy on that thing. So I have just quantified my energy flux vector. So that's the first balance that we're going to have. Essentially, we're going to have that net rate of energy by convective and molecular transport. Okay, I apologize. Sorry. My phone calls go to my computer. Oh, shush. Wow. Okay, stopped. My phone calls go to my computer as well. Unfortunately, that sometimes it's useful, sometimes it's not. All right. So net rate of energy by convection, molecular transport, and work done by molecular transport. Okay. So that is the first part. One thing that I did not describe by that energy flux vector. So this is essentially what is described by energy flux vector. I might have some work done by external forces. Okay, so I have to add that to my balance. And I should also look at any kind of production or sink for my energy inside. So I'm going to, inside my system, so I'm going to say net rate of energy production. In particular, I might have a chemical reaction where heat is a byproduct. So I do have to take that into account. So when I sum all of that up, at steady state, I should have a 0. Okay? And if it's not a steady state, then it's a net rate of change in time. Okay? So that should be simple enough. Now, so this is the first piece. This is how to set up the equation. Second piece is any boundary condition that I might have. So boundary conditions that we will actually encounter are as follows. The first one is simplest one. It's setting an energy, which is the Dirichlet boundary condition in differential equations. That's basically setting temperature to be a certain value at certain surface. Okay, so setting temperature to a specific value on a surface. Second thing that I could specify is a flux, okay, that is normal to that surface. And then I also have to look at the boundaries between different materials. Okay. So at boundaries between different materials, this is where we will have to look into what is the thermal conductivity of the material. Okay. And essentially, if I have similar material, or similar two types of materials in contact, I can assume that my temperature is continuous across that contact. Okay? Even if I have slight differences in the rate that material is transferring temperature through. But if I have two vastly different materials, in particular if my materials are actually transferring things at the rate that might be different by an order of magnitude, okay, then I sort of don't have time to catch up, okay, and don't necessarily have time to, so I have to account for these different rates across the surface, and for that we will use so-called Newton's law of cooling. So not only that these different materials will have different rates of transfer, there will be a rate of transfer across that boundary as well. Okay. So, and of course I will depend on the difference between the temperatures on the two different sides. So if I have for two similar materials, and by that, really, I can go by fluid-fluid or solid-solid interface. I can assume the following. A, temperature is continuous at the boundary. Oops. And also heat flux at that boundary or normal to that boundary is continuous as well. So heat flux normal to the boundary in other words, my Q dot N, when N is normal for the boundary, right, is continuous as well. If I have two materials that have vastly different, or for instance, thermal conductivity that is different by an order of magnitude, okay, I'm going to have, so for fluid-solid boundary, I can assume that I have temperature of the solid, temperature of the fluid, and they don't have time to basically immediately or instantaneously equilibrate. Okay. So for that, I will use basically my Q is H, or transfer normal to the boundary, is some coefficient of transfer H times the difference . So this is Newton's law of cooling. Newton left no piece of this course untouched. Newton's everywhere. So this is what I call heat transfer coefficient. Alright, so this is basically how we will set up the problems. Let's actually finally work on a problem. So my first example is going to be from chapter 10.4. hint in general, just because I'm skipping to the fourth chapter, that doesn't mean you should not work through the first. Again, all of the chapters in chapter 10, all of the sub sections in chapter 10 are basically problems that are solved. So I will solve a selection, but you should definitely work through the others. So this time we will actually, so for this problem, we will look at our Couette flow. Okay. So my Couette flow, just to, so this is my radius r, and this radius here was 1 minus kappa r. And I have the outer boundary rotating at constant rate omega. So again, this is angular velocity omega. The way angular and linear velocity are related is linear velocity is omega times the radius, right? And we know that basically, so this was my Couette flow. And we will add heat transfer here. So our initial discussion of Couette flow was isothermal. Everything that we did in chapter 2 and 3 was isothermal. Okay? So now we will add to it. So we will essentially couple transport. And the way we will couple transport is that I'm going to add that this inner boundary is at temperature T0. Okay? And this outer boundary is at temperature TB. And what I will refer to B is this thickness, essentially kappa R of this annulus. So this is annulus width. So again, inner cylinder is static. So static inner cylinder. And outer one is moving with constant angular velocity omega. And now, in addition to that, we have inner and outer cylinders at different temperatures. Now, what would happen? So now I actually have basically velocity. And if I just remember how velocity looked like, so my velocity was basically, so here it's 0, and then it increased until I reached my omega on the boundary, right? So that was my Couette flow. And we actually had an expression for it, okay? So my V, this was a theta of R, was omega R, R divided by kappa R minus kappa R divided by R divided by 1 over kappa minus kappa, okay? And VR, VZ were 0. So this was our solution from chapter 3, okay? I'm just stating. If I had a static fluid, okay, and I look at this Couette flow and I imagine it's actually this radius R is pretty large, so when I kind of zoom in onto that boundary, I can imagine it's actually a straight piece because its radius is so large. What would I see? What type of temperature? So let's say that there is no fluid movement at all. I haven't started moving fluid. What would my temperature distribution look like? It will go from T0 to 2B. And now I actually expect some disturbance, nonlinear disturbance to it. And I'm wondering, well, what is this nonlinear disturbance to it, given that basically this is my velocity distribution that I have, so I have all of that convective energy and stuff moving into my volume, fluid volume as well. So let's take a look. So essentially, if fluid was static, what I would essentially have is that when I zoom in, I would have T0, TB, okay? And let's say that this is my T0 and this is my TB, so I would have sort of a linear distribution between. And now it's not going to be linear, but basically with moving fluid, I expect some, so moving fluid non-linearly affects my temperature distribution. And I'm wondering, well, what is this effect? So in order to solve for this, I will indeed actually zoom in. I will assume large R, okay? Assume R large and curvature of the entire system is small. So I'm actually nearly dealing with a slit. Okay? And I'm going to call this direction of that slit X. So this was my previous R direction. And this direction will be Z. And I'm also going to linearize my velocity as well. So basically I'm going to say, so here on the inner part I have velocity static, then it's kind of increasing all the way up. So I'm going to linearize my velocity, Vz, and I'm going to call it Vz of x now. And it's going to be omega r x divided by b, where b is this thickness of the slit. So indeed, on the where x is 0, that's my inner cylinder, it's going to be 0. And where x is b, I'm going to have omega r, and that's my linear velocity at the outer cylinder. Okay, so linearized velocity profile. Okay, so if I imagine a little element in this system, okay, so this is my x plus delta x, z plus delta z. I have to essentially collect everything that is coming through into this element through the boundaries. Okay? And what I'm actually looking into is this energy flux E. Okay? So here we will disregard, so when I look at my balance, I have stuff that was quantified by my energy flux vector, which is convection, any work done by molecular forces, okay, and the actual just the temperature gradient driving things. Okay. And then I have this work done by the outside forces, which here we will neglect. And we will assume no reactions, so I don't have any kind of creation of energy within this volume. So basically all I have to look at is balance of this energy flux. Okay? So I have to look at stuff, what is coming through, so that vector E, okay, it has x and z components in this coordinate system. So this little direction that I show here is which direction? X. So this is going to be quantified by Ex, what is coming through, right? And basically, in this direction, I'm going to have Ez. Okay. So in order to balance, I'm going to quantify the, so basically the length here is delta Z times some length in the third direction that I'm just going to put as W or L or anything. It doesn't really matter. How about I put it as W? So this is sort of width into the paper, so to speak. So that my units work out. And my EX evaluated at X. Okay. And I'm gonna subtract what comes out on the upper boundary, so minus delta Z W, EX evaluated at X plus delta X. So this is similar to momentum, just actually simpler because I have a vector. I don't have a tensor. So my E is a vector. I don't have tensor stuff. Okay, and then plus, on this other boundary, this width here is delta X, and I'm gonna also put times a W, EZ evaluated at Z. So that's what's coming in at the lower Z boundary, and what's coming out is delta XW EZ evaluated at Z plus delta Z. And that is equal to 0. Again, because we neglect outside forces. We neglected gravity in our solution for velocity as well. So that's consistent. And no production. So no reactions or anything that could produce heat. Speaking of stuff that you cannot read on a movie, right? So we neglect work of the outside forces and there is no production. So this is our balance. Well, then we've done more complex stuff in momentum, so this is going to be easy. I divide by my volume, okay, so which is delta X, delta Z, W, and when I divide, I'm going to also send my delta X to 0, so I'm going to have minus EX, X plus delta X divided by delta X minus EZ, Z plus delta Z divided by delta Z is equal to 0. So the way PDEs come, this is a very simple one. I'm going to send delta X, delta Z to 0. And when I do, I'm going to have a very simple PDE. It's going to be partial EX, partial X plus partial EZ, partial Z is equal to 0. Okay, so just like this, so my PDE looks simple enough, but my E, my energy flux, is not necessarily simple. So when I think about Z component of it, let's see what Z component is. It's going to be my energy times Z component of velocity. This is where I had just velocity vector. So I just look at its Z component. Plus Z component of my viscous stress tensor dot V and plus QZ. When I have a viscous stress tensor dot vector, that's really matrix vector multiplication. Okay, so this here is tau Z V, tau ZX, sorry, Vx plus tau ZY Vy plus tau ZZ Vz. Cool. And QZ. Now let's look at what we can actually think of as 0. So my Vx, Vy, Vz, Vy is 0, right? That's a simple one. We had x, and so I have no velocity in x direction, so Vx is 0 as well. The only one alive is the one in VZ direction. However, this tau ZZ will involve derivative with respect to Z of VZ. Okay? And I don't have Z dependence of VZ. So this entire term here will be 0. So essentially, this part is 0, this part is 0. This part is non-zero, but this part is 0. Okay, because I don't have Z dependence of VZ. VZ is VZ of X. So that's great. This disappears. Okay. Now, this portion QZ, can I have, so my gradient is in X direction, my temperature gradient. Okay. So do I expect any flux of heat in Z direction? No. Otherwise, I would have a very cool heat generation going on. Okay, there would be some perpetuum heat mobile. Okay, there will be some generation of heat in the circle. So this is going to be 0 since there is no T difference in Z direction. So there's nothing to drive my basic Fourier's law in Z direction. Okay? Just give me 1 second to finish off. And then when I actually look at partial EZ, partial Z, okay, I'm going to have partial Z of this term up here, which has VZ in there. And VZ depends only on X. So this long story was to actually conclude that partial EZ, partial Z, luckily, is 0. That's going to make solving this problem way simpler. So what we are left with is partial EX, partial X is equal to 0. And we will complete that next time. All right. See you on Friday. And I will post all of the slides and everything, and if I don't, yell at me tonight, okay? I mean, yell at me. Send me an email. Please don't yell. Yes.
How was your return?
It was great. What I found in the country when I came back was not.
That's pretty good.
Anyway.
Welcome back.
Thank you.
Are we meeting tomorrow?
Yeah. Yes.
Okay.
We are at 1 o'clock. Yeah. We're at 1.
No. I wanted to ask you, is our goal to translate the entire MATLAB code? Or not?
I would go like this. I would, at this point, translate pieces that we need already.
Yes. Yeah, the things to build are not. Because I've been
It's
thinking
not a lot of code, I don't think.
No, that's right. I've been thinking of ways to make a nicer structure.
Okay.
Like with objects. We can discuss it.
Okay, sounds good. So we need to draft a master plan.
Yeah, I've been thinking in different ways, but yeah, I think objects is the way to go.
Okay,
So,
sounds
we'll
good.
see.
Professor, I have a problem conversion from the momentum flux to heat flux. So this tau ZZ we're talking about is a velocity.
This is my regular viscous thing, right?
Okay.
So tau ZZ will have 2 dVz dz in there. And since VZ doesn't have dependence on Z, it's going to be 0. So VZ is not 0, but dVz dz is 0.
Is there? Yeah. Okay.
So that's my standard tau ZZ, like the way we're used to. And the way we're going to solve this, we're kind of decoupling. So we will say, okay, I know my velocity distribution. And that's that one that we solved for in chapter 3. And knowing it, then I can calculate all of these things. So I will assume that whatever temperature change I actually have is not affecting my viscosity. Right.
I see.
So it's not that large to actually change my viscosity, because that would actually change my viscosity. It would change my mu, so it would change my tau as well.
I see.
And that's one key simplification in solving this. And even if you don't assume that, when you're coupling later, if you do that in your research, you will actually still have to step by step, like you will, for the time being, assumed that mu is constant and it's whatever it was at the previous step. Then you will calculate the heat transfer and maybe possibly, based on the temperature you have now, change your mu and then move on.
Okay.
But you will conceptually keep it still in this form that we used for isothermal flow.
I see. Okay, and my second question is that in here, you just assumption that the velocity is linear, right?
Yeah,
But
so we
it's-
just simplified. And again, if I have a very large R, that means also that kappa is rather small, so you can actually see how that's.
Okay, I see.
Yeah.
Okay, thank you.
my email about Baker Hughes, so I guess, word got through somewhere down the line. And
I
they,
didn't know, I just pushed on yesterday, he said he was going to.
good, thank goodness. Too bad you can't. Oh well, take what we can get.
if we did, we wouldn't have that.
Okay, we'll take what we can get. Alright. Well, good deal, good deal. So as soon as we get that signed, we'll have the money deposited in the account. So I'm sure Jessica, now that she's in the loop, she will be on it because she sent us the first things. So that's great. Let's see here. Okay, so I replied to Daniel about Abacus. That'll pretty much spend down the rest of what we have in your 19 account. Let's see. You still have 46,328 in your 30 account, so that's great. 2537 in your dark code. Let's see, and we got some more money returned to our NSC account for the transfer that we did with I guess it was Nick and Jim Chow. Let's see here. Oh, and they added for the Abhishek's data oil, they added $1,000 for travel.
Yes, I saw that.
So I updated that. And this one's the same. Yeah, that's that.
Good.
Okay, so I sent the agreement for Baker Hughes. Let's see, what else do we have? I cannot think of anything off the top of my head. Do you have anything?
I had nothing, no.
Okay.
No.
Alright.
You got the money from Baker, was it?
Okay, perfect. And I have these leftover Cokes and Topo Chicos. Did you want to take any of those? I know your wife loves Topo Chicos.
Yeah.
Let's see. I think I have a bag. Better than carrying them all around.
Yeah.
You don't want any of the Cokes?
It's funny, we bought a 12-pack of Sprite from my son's birthday party. It was still sitting in the fridge, I'm just gonna bring it in just a moment.
Okay.
Because we've given up drinking sugar, so.
Yeah. I don't drink Cokes anymore. I drink like a Central Market has like a flavored water or something, and it's only 90 calories for a can, whereas that's like 200 calories or something. So, do you want any of these chips, peanuts? It's like roasted.
Those are honey roasted peanuts.
Want
I
any of those?
might just stick a handful of honey roasted.
These two. Otherwise, I was thinking I'll probably just
Yeah,
run downstairs.
put them upstairs, that's
Okay.
fine. Okay,
Alright, great.
cool. All right, well, we're all set.
Okay,
Okay, so I'll see you next week.
alright. I'll have to work for you.
Oh,